Hi, we're excited to share with you our robotic manipulation final project, ShelveBot, fast pick and place in human form factors.
In recent years, there has been a renewed interest in the application of mobile-based manipulators to tasks that take place in human-centric spaces. Repetitive pick-and-place activities regularly occur in spaces built to human form factors like kitchens, playrooms, and existing production lines in warehouses.
Most current robotic systems fall short in this regard. They require that the environment they operate in is fit to their form factors, resulting in significant overhead that precludes a host of applications. We believe that mobile-based manipulators hold great potential for operating in human-centric task spaces, since their mobile-based and arm-like structure can often achieve motion that is comparable to that of humans.
To that end, we present a bimanual mobile-based robotic manipulator for fast object reorganization in shelves. We centered our work around shelves as they are a cornerstone of human form factors with which we regularly interact, often in repetitive ways that could benefit from increased autonomy. Additionally, reorganizing objects quickly presents interesting planning and control challenges as a result of the need to move quickly in a constrained space.
Related work inspired our approach. For example, our exploration of hierarchical motion planning that employs local optimization for path planning was inspired by TRI's grocery store mobile manipulator. Our use of the antipodal grasping heuristic stemmed from the successes it found in prior work, such as DexNet. Similarly, we chose to represent 3D object geometry using point clouds due to our prior experience integrating them with antipodal grasping and prior work demonstrating their efficacy for manipulator platforms operating in home environments.
Our motion planning system leverages both sampling and optimization-based methods to effectively plan across a large environment with constrained target locations. It begins by heuristically selecting the gripper with which to grasp the object of interest, choosing the closest one. It then solves an inverse kinematics optimization problem to find the full body joint positions that would align the chosen gripper with the target. A global plan to navigate from the current joint positions to the desired ones is generated using RRT. Then local plans for each pair of RRT points are created using kinematic trajectory optimization. Using Topra, we reparameterize the resulting local trajectories to traverse them as quickly as possible.
Using pre-computed point clouds with normal vector estimates, we sample antipodal grasp candidates and score them with a custom cost function that incentivizes the gripper to keep its x and y axis aligned with the direction in which the robot approaches the object. Navigation from the pre-grasp pose to the grasp and from the grasp pose to the post-grasp is all achieved through inverse kinematics and kinematic trajectory optimization.
We create a simulation environment separate from that in which we shelve objects to record perfect point cloud data for the objects of interest.
We formulate each of these modules in a symbolic programming framework such that it is easy to mix and match them to create high-level plans. Here's a real-time demonstration of our system in action.
After choosing the best grasp pose, we use trajectory optimization with no collision constraint. Then we slightly move back and pass the control to the motion planner. For grasping trajectory, we increase the density of the collision checking time steps at the end of the trajectory. For placing the object, we solve another trajectory optimization problem with collision constraints, in which we weld the robot's gripper to the object to avoid collisions with the shelf. Throughout the development of our system, we learned some valuable lessons. First, working on a new platform is challenging. For example, when we first started using PR2, we had to rewire all these joints since the order of the joints and actuators were not the same in the URDF. So for example, the inverse dynamics controller would move the wrist when we commanded the shoulder to move.
While defining behavior goals in terms of optimizations is a great tool, it provides no guarantees of convergence, and fine-tuning costs and constraints can be time-consuming.
The transitions between planning methods that use different simplifying assumptions to make a problem tractable can be a larger implementation hurdle than expected, especially when pre-computing trajectories without real-time adjustment. Future work includes stress testing our system and improving it to ready for deploying on real hardware. Two main areas we'd focus on would be increasing the reliability of our system by adding the ability to plan around static and dynamic obstacles.
Another area of improvement for deploying on hardware would be to generalize our perception system so that it no longer relies on privileged information.
Finally, we would like to leverage our symbolic programming interface to connect our system to a high-level task planner based in programming synthesis or large language models.
We would like to express our sincere gratitude to Professor Drake, the technical staff, and CIM instructors for their dedicated guidance and insight. Thank you for your time.